We're going to take the ideas from our last class, the derivative at a point, and take it a little bit further. So let's take a look at this graph that you have in front of you. Our function, we'll call that f of x, is the red curve. You can see on the red curve, I've drawn a bunch of lines at specific points on it. These purple dots control the slope of that line. So what I want us to do is move those purple dots so that each one of those lines is a small little mini tangent line. For example, right now, this point already is controlling a tangent line. That horizontal line right there is tangent to the red graph. Moving on to the next purple point, I need to control that line a little bit. What I'm going to do is make it just right so that that purple line is tangent to the red function. This purple dot is controlling the slope of the tangent line, which means that whatever this value is, it looks like, you can see this number is -1, so this looks like it's about -0.7. Looks like it is the slope of the tangent line when x is about -4. It's not exactly -4, but about -4, which means that is the derivative at that point. And so I'm going to keep doing that for the rest of these points. You can see that's not tangent. This is getting better, better, better. This one's a little bit tricky, but we kind of want to match it up just right. So that black line appears to be tangent to the red line. You can see what we discussed last class, the local linearity, where the red line appears to be straight right on top of that black line. I'm going to do that for all of these other points. One thing to notice is it looks like this purple dot and this purple dot are at the same y value, at the same, which means the two tangent lines, this purple and this red one, they appear to have the same slope. So it looks like the derivative at the point where x is, whatever that number is about the same as whenever x is, whatever that is. This one, this next purple point, looks to be already right because that blue line does seem to be tangent. This next one, no, that's not going to do it. I need to move up here. And so you can see I'm just controlling it to make that green line tangent. I'm going to keep going up here. And you can see that all of these tangent lines are matching up pretty well. Okay, that appears to be done. Now let's talk about what we have here. I want you to notice what the function was doing each time the value of the derivative at each point turned out to be positive. So that only happened 3 times. I only had 3 positive derivatives. There were only 3 points on this curve where the derivative was positive that I marked. But what was the function doing in that time? It looks to me like the function was increasing. I could say is increasing. And that's a big deal. That's a huge connection to make. The derivative is increasing every time the derivative is positive for the entire time when the function is increasing. Or you can say that the other way. The function is increasing every time the derivative is positive. On the other hand, if you look at these points down here where the derivative was negative, look at the function over that time span, over that stretch of x values. You can see the function is decreasing here. The function is also decreasing here where the derivative values were negative. So there's clearly a connection there between the positive derivative and the increasing function, and a connection between the negative derivative and the decreasing function. Now we're going to look at the few points where the function was neither increasing nor decreasing, these min and max points that are spread throughout. Notice how each one of those times the derivative was 0, which makes a whole lot of sense. That tangent was a flat line, flat horizontal line, which means that the slope must be 0. The line we're going to use a lot throughout this year is the phrase horizontal tangent. The function had a horizontal tangent at those x values. Some of those points were min, and some were maxes. I'll use the actual word. Minimums isn't a word. Minima is the way you pluralize minimum. Okay, just a quick word about language and notation here. What we've done is we've plotted a bunch of points where the input, the x value at these points, is just an x value, and the output, the y value of these purple dots, is the derivative at that point, the derivative of f at that point. Well, remember back to Algebra 2, we learned there's a word for that when you have a set of inputs and outputs that go with them. That's called a function. So this is what we call the derivative function. Meaning it is those purple dots put together, and of course all of the in-between dots that we didn't graph here, but that would connect them, is what we call a derivative function. Using function notation, we would call it f prime of x. Not f prime of c, which is the derivative at one specific point, but f prime of x. All of the derivatives at all of the points taken as a group. That's the idea of a function. So that notation f prime of x is big. We're going to use that notation all the time, and I really, really want to highlight what I just said about the difference between f prime of c and f prime of x. F prime of c is the derivative at the instantaneous rate of change, or the derivative at a specific x value, where c is a number, f prime of 2, f prime of 7. F prime of x is a little bit more abstract. It is all of the rates of change at all of the different possible x values described as a function. So we're going to summarize what we said in the first couple of slides about those derivative functions. The set of values of f prime of c for every possible value of c in a function's domain is called what we just said, the derivative function. And its notation is f prime of x. Again, different from f prime of c. At any moment in time on f of x, and whenever I say moment in time, I'm talking about an x value. So at any x value, if f of x is increasing, right, the original function is increasing, then f prime of x must be positive. On the other hand, if f prime of x is negative, that means that f of x must be decreasing. Notice how I said that those two statements, I said them in each direction, because both ways of looking at it are true. If you know a function's derivative is negative, you know the function itself is decreasing at that moment. But you can say it the other way too. If a function is decreasing at any moment in time, then f prime at that particular x value is negative. And the derivative function, f prime of x, will have a 0 at any value where f of x has a horizontal tangent. Including relative mins and maxes. So what we're going to do is use that idea, use those three ideas, positive derivative, negative derivative, zero derivative, to sketch a graph of f prime of x for this function. Now, there's no equation that goes with this function, or at least we don't care about it. We don't need to know the equation of f of x in order to sketch f prime of x. What we're going to do is look at a couple of key points on here. For example, this point right here, where x is, looks like negative 1.5, it looks like there's a relative min here. So there would be a horizontal tangent, meaning the derivative should be 0. Now, for all the points to the right here, the function is increasing, which means the derivative is going to be positive. Now, it does seem to be getting a little bit, it's getting steeper. So the derivative starts out at 0, then it starts getting bigger and bigger. It starts going up faster. So I'm going to draw a curve for the derivative that increases. Notice how the function is steeper here than it was here, which is why the derivative is higher here than it was there. For all the values before negative 1.5-ish, I can see that the function, the red function f of x, was decreasing, so the derivative values must all be negative. So it would look something like this. I'm not worried about getting it numerically exactly right. I'm worried about the shape right now. Okay. Next up, for the next section here, the derivative is going to have to be positive because the function is increasing. And more than that, I can see that the derivative, remember, is the rate of change at any given moment. Well, for a straight line, the derivative never changes. The derivative of a straight line is always going to be the same because the instantaneous rate of change at every point on a straight line is the same. The slope of this line is 1, which means that the derivative over this entire section must be 1. That, by the way, is how I knew to end my point. From the first section, I knew to end it at 1 because I happened to have noticed this hint that told me that the derivative is continuous, which meant whatever I ended up here had to be the same here. And then if I look at this function, the derivative, this function for this section is still increasing between 2 and 4, but it is increasing at a decreasing rate, which means that the steepness is going down. By the time I get here, the function is not changing at all anymore. So the derivative must be 0. So between here, where the slope is positive, and here, where the slope is 0, my derivative must decrease. I'm trying to draw a straight line. Didn't really succeed. And then between 4 and 6, because this function is constant, the derivative must be 0 the whole time. And so this blue line is my best guess at what the derivative of f of x, what f prime of x would look like. I actually do have it stored here. This is what it actually looks like. See that blue line that popped up. The next couple of slides, we're going to get into something very, very specific. Look at this red function. Do you recognize it? Hopefully you do. It's a sine curve. And if you were to imagine connecting the dots of the purple function, f prime of x, do you recognize that one? Not the end of the world if you don't, but hopefully you do. It's a cosine curve. So it's interesting. You might not have expected this or had no reason to know it was going to happen, but the derivative of a sine curve is a cosine curve. It's worth remembering. We'll talk more about that next week. Here's another one. We're going to drag these purple points. Notice how the line down here is increasing pretty quickly, which means its derivative is going to be pretty high. Actually higher than I can get to, I think. Again, the function is increasing here, so the derivative will be positive. Here the function is flat. The function has a horizontal tangent, so the derivative must be 0. And now the function is decreasing, so the derivative at x equals 2 must be negative. Here, the horizontal tangent means the derivative at 3 is 0. And now the function is increasing when x is 4, which means that the derivative must be positive. And then later on, it's even steeper, so it's even more positive. We'll take a look at these two functions. The original function, the red one, hopefully you can recognize that shape. That's a cubic function. And its derivative, f prime of x, just by plotting those points, hopefully you notice that pattern. That is a quadratic. That looks like the makings of a parabola. So we saw on a couple of pages ago that a linear function, a straight line, whose degree is 1, has a derivative with degree 0, a constant. And here we see a cubic function, degree 3, has a quadratic derivative, degree 2. What do you think a quintic function's derivative would be? G of x is a quintic function, 5th degree. G prime of x would be 1 degree less than that. I don't know why I started writing. We call that a quartic function. This is a pattern we'll talk more about in the coming weeks, but it is worth pointing out right now that it's an easy thing to spot.